About reaction mechanisms. So a reaction mechanism is really looking at what molecules are interacting and how are they interacting, and then what products are you making. So looking at very specifically those interactions. And this can happen in one step, or it can happen in a series of what we call elementary reactions. So we can describe the molecularity of these elementary steps. So these are like individual steps of a multi-step process. If you have one reactant molecule, we say this is unimolecular. So here we have A going to products. This would be the rate law. We can determine the rate law from these elementary steps just based on the stoichiometry. This is really like a hypothetical explanation for why we see the experimental rate law. So we do this reaction, we figure out what the rate law is, and then we go back and try to explain why we see that experimental rate law through these reaction mechanisms. And so because this is a hypothetical explanation, we can use the stoichiometry of the reaction to figure out what the rate law is. Now you can't do that for the overall reaction, only these elementary steps. So I have to take that overall reaction and break it down into smaller steps. So if you have one reactant, we say it's unimolecular. If you have two reactants in that elementary step, we say it's bimolecular. And if you have three, it's called termolecular. Now termolecular reactions are going to be pretty rare. In order to get three reactions to line up perfectly and interact all at the same time is going to be a very rare experience. You're going to see a lot of unimolecular and bimolecular, but not so many termolecular reactions. Again, you can determine the stoichiometry, the rate law from the stoichiometry. So if you have one reactant, the rate is equal to K times A. If you have two A's, it's K times A squared. If you have A and B, K times A times B. So it's always K times reactant times reactant. You don't even have to worry about the products. We're writing the rate law based on the reactants. There we go. Molecularity, right, tells you how many molecules are involved. Usually these are multi-step processes, and so we will look at adding up all of the elementary steps. That's going to give us the overall reaction. Sometimes you have an intermediate. An intermediate is something that's made in one step and used up in another step, so it's not going to appear in the overall reaction. It's the product of the first step and then the reactant in the second step, something like that. So let's do a couple examples of these problems. It's been proposed that the conversion of ozone into O2 proceeds by a two-step mechanism. So here's our mechanism. This is step one. This is step one. This is step two. And they want us to describe the molecularity of each elementary reaction. So is this unimolecular, bimolecular, termolecular? What do we have here? So for step one, I have exactly one reactant. So we're going to call that one unimolecular. I'll type this for you. Let's see, unimolecular. And if I have two reactants in the next step, 1, 2, right, that's going to be right up here. This is where I'm getting this unimolecular. This one would be called bimolecular. Cool. Oh. Now, can we write the equation for the overall reaction? All we're going to do here is add up all the reactants and then add up all the products. So everything on the left-hand side here, I'm going to add all these up. I've got O3 plus O3 plus O. We've got O3 plus O3 plus O, and then on the product side, I have this. I've got O2 plus O plus 2O2. So if I simplify that a little bit, O3 plus O3 is just 2O3 plus O, and then on the product side, I have O2 and two O2s, that's 3O2, and another O. And now you can see that I have O in the beginning here and O at the end there. So O is a reactant and it's a product. It's actually what we call an intermediate, right? Because it's made in one step and then it's used up in the next. So it's the product in the first one and the reactant in the second one. So they cancel in the overall reaction. I just end up with 2O3 goes to 3O2, and my intermediate is O because it's a product and then it's a reactant. So just to summarize, this has one reactant, so it's unimolecular, two reactants, it's bimolecular, and then the second part here, we added everything on the left, added everything on the right, combined like terms, so I have two O3s, I've got three O2s, and then cancel things that are the same on both sides, which was the O, and that O was an intermediate because it's made in the first step and used up in the second step. Okay, so moving on. So a lot of times when you have a multi-step process, you're going to find that those steps don't always happen at the same rate. you usually have one step that's going to happen a lot slower. And we call that step the rate determining step. You're only as fast as your slowest step. So this is the slowest step in a multi-step process. And then the overall reaction can't go any faster than that. That's going to determine how fast the reaction happens. So in this diagram down here, you can see there's two toll plazas. In the first picture, you can see the cars are kind of getting backed up on this first step. This is the rate determining step, toll plaza A. Once you get through there, reaction goes pretty fast. You can blow right through toll plaza B. For the second diagram here, you can see the cars are going pretty fast through toll plaza A, but then they get stuck at B. So B would be the rate determining step there. So I'm just going to circle these rate determining steps. So here, where the cars are getting backed up, that's the slow step. And then over here is where the cars are getting backed up, that's the slow step. And that happens in reactions all the time as well. So let's see a couple examples of these. Here's an overall reaction, and they give you the two reactants, you got two products. But then when you do the experiment, you find that this is the rate law. So remember how we found this rate law? We're going to take these two reactants, we're going to change their concentrations, measure the rate, then change the concentrations, measure the rate, take a ratio of those rate laws, solve for M and N, right? So we found that basically it's zeroth order with respect to CO and second order with respect to NO2. Now, this rate law doesn't match this overall reaction. And so that's a clue that this is not happening in one step. Like this is not just a single step reaction. If so, then CO would be part of the experimental rate law, but we don't see that happening. So CO is not necessary for this reaction. Sorry, CO is necessary for this reaction to occur, but the rate doesn't depend on its concentration. So that's what we mean by it's zeroth order. I can do whatever I want. As long as there's a little bit here, this reaction is going to happen. And so then what we do is we propose a mechanism. We say, right, maybe this happens in two steps, and here are the two steps. So let me just pause for a second. I'm not going to ask you to propose a mechanism. You'll do that in organic chemistry. Right now, we're going to have an overall reaction. I'm going to give you a mechanism, and it'll be like verify that this is the rate law, or if this is the mechanism, try to determine what the rate law would be, what the experimental rate law would be. So you're not going to have to come up with this part on your own. This will be given to you. So suppose this was the mechanism. I've got NO2 plus NO2. This first step is slow. That means this is the rate determining step. That means after this reaction, this first step happens, then the reaction goes really fast. So this is the slow step. So that's what's going to determine the overall rate law, which is why step 2 here, it doesn't really affect things. It's going to be so fast compared to the other one that we don't even have to worry about it. If the first step is slow, that's all we worry about. The intermediate in this case, let's see, can we find the intermediate in this reaction? Looking at my products, I've got NO3 here. That's the product there. I've got NO3 as a reactant. So NO3 is going to be our intermediate for this case. So NO3 is our intermediate. And so can we predict what the rate law would be for these elementary steps just based on the stoichiometry? We can do that. So if a reaction is elementary, so if this is a hypothetical explanation for how the overall reaction is happening, then the rate law is based directly on the molecularity, which is basically the stoichiometry of your reaction. So for this first one, I would have like rate 1 is just going to be, I'm going to call this K1, the first rate constant, times NO2 times NO2, which is just NO squared. And then for the second one, rate 2 would be, I'm going to call that K2 times NO3 times CO. So if rate 1 is the rate determining step, then that's what the overall, there we go, that's what the rate law, the experimental rate law should be. And so that's what we did there. We have an overall reaction that we know this is happening. I mix these two things together, I get this. We do the experiment, we figure out that's the experimental rate law, and then we explain it with this mechanism. And then all I did here was just verify that if I were able to write the rate laws for each one of these intermediate steps, of these elementary steps, this first step is the slow step. It matches the rate law directly. Now, another thing that we should mention, and we'll see this in the next one, is that you cannot have an intermediate in your rate law. So if the second step is slow, this process gets a lot harder. We'll do that one next.